Hello, chemistry class. I am not with you today as I'm with my Rocket kids in Washington, D.C., but I do have a few things to share with you today so that we can learn about those and come back and make some ice cream next class. So today we're going to dive into two topics. That's thermal equilibrium and then endothermic and exothermic reactions. It's going to be helpful for you to get out that hot and cold energy diagram lab if you didn't already turn that in, as those energy diagrams might be helpful to look at as we talk about these things today. So the first topic that we're going to dive into is thermal equilibrium. Now, thermal equilibrium is a lot of what it sounds like, right? Think about when you get into your car on a cold day, right? It takes a while for your cold seats to warm up, but there's a point where they're no longer cold to you anymore, right? So the definition of thermal equilibrium is that this is when two substances are at the same temperature, which means this is when heat transfer is equal. When our heat transfer becomes equal, right? So there's a point where, right, if you put your hand on the bench top and it's cold, right? At some point after you've left your hand there for a while, it's no longer going to feel cold to you. And this is because you've reached equilibrium, which is where the heat transfer between your hand and the bench top becomes equal. So what we say is that this is where, right, we use the variable Q. So the amount, right, the positive Q of our system is equal to the negative Q of our surroundings. And the reason for this, right, is that maybe your hand is the system and the bench top is the surrounding, but as much energy as you give the bench top at the point where it no longer feels cold, the bench top is also giving you that much energy back, right? So what's important is we can think about this if two substances are at different temperatures. If two substances are at different temperatures, our heat flows from hot to cold, right? Something that's hot, and it flows to something that's cold, right? We have our little ice cube. We might have some fire going on over here, right? But whatever's hot, the energy is going to flow from that to our cold thing, which means that our hot object is going to have that negative Q value, while the cold object has positive Q, right? It's gaining energy, it's losing energy. And however much it's losing, that's the amount that this gains. And that happens until they reach the same temperature. Right? And that is our equilibrium. At this point, our Q's are going to be equal, right? We don't have one that's gaining, we don't have one that's losing. They each just have the same amount of heat. Now, this is important. Think back to physics. and we had a law of conservation of energy, right? So don't forget, energy is never created or destroyed. It is only transferred. Is never created nor destroyed. Only transferred. Okay, so last time, right, we were talking with those hot and cold energy diagrams about having a system and having a surrounding, right? Where your cold pack or your hot pack is the system, and then we have these surroundings. So let's think for a second about that. System versus surroundings. Okay, in chemistry, as we talk about this, the only thing that is going to be your system is the chemical reaction. Now, if you're like, well, Miss Craig, what if I want the chemical reaction to be the surroundings? That would be fine, right? But it's easiest to think about our chemical reaction to be the system because the surroundings then have to be everything else. And when we say everything else, we really mean everything else. This is the rest of the universe. So it's not a small everything else. It's not just, you know, my hand or something else, but it's the entire world, right? It's our universe. So we can draw a picture of this and think about it this way, right? We have our system. Now, there's two ways that this could go, right? If our system is hot versus if our system is cold. But everything outside of that system is our surroundings. If my system is hot, right? Energy is gonna flow from my system to the surroundings, right? Where the inside is hot and the outside is cool, which means our system's gonna be losing that heat and our surrounding will be gaining that energy. On the other hand, if our system is cold, right, it's gonna be pulling energy in from the outside to reach equilibrium. So here, this would be our positive Q, and our surroundings in this case would be our negative Q. So we have both reaction types, right, where we have energy going in and energy going out. But we actually have names for those. We have names for these things, right? So you were briefly introduced on that hot and cold energy diagram lab to the words endothermic and exothermic, right? It said that on the back, and you started to think about what it means for something to be endothermic and what it means for something to be exothermic, right? So we're gonna break that down a little bit today. Now, when we talk about something being endothermic or exothermic, it's important that we talk about enthalpy. And enthalpy is something that is new to us. And we're specifically going to be talking about enthalpy change. Enthalpy change. Okay, so we have two types of reactions we're going to break down. We're going to start with exothermic reactions. Now, there are a couple ways to help you remember, right, the difference between endothermic and exothermic reactions. One thing that I like to think about is that exo kind of sounds like exit, right? And this is where our heat is going to be exiting the system, right? So we have exothermic reactions, and we're going to compare those to our endothermic reactions. Now, endothermic, on the other hand, these are cold, right? Like an ice cube. Okay, so we can talk about first the physical properties of these, right? An exothermic reaction feels hot. It feels hot. If you have an exothermic, right, we want an exothermic for our hot pack. That was what we learned last time. Which means on the other side, we can say that endothermic reactions feel cold. Right? These are cold feeling reactions. Okay. Now, we gotta be thinking about if energy is produced, released, absorbed, required, all those words. And this was also on the back of that worksheet. But for exothermic reactions, our heat energy is released or produced. Now, one of the reasons that we use the word produced here is that sometimes people will write this in an equation, right? In a chemical equation. They'll say plus this much amount of heat on the reactant side. On the product side, right? You're producing it, so they put it on the product side in a chemical reaction, which we'll talk about in a second. But what this means, if heat is produced, that if we have our system, right, what we were just talking about, and we have surroundings, this is going to lose heat because it's giving off heat to the surrounding systems. It's giving it off to everything else, right? So if you drew an arrow, our heat flow goes that way. Now there's a couple notations that go along with this. The first notation is what we call delta H notation. Now you might be like, Ms. Craig, what the heck is delta H? So now we're going to come back to this word that we started with at the beginning, enthalpy. Now, what enthalpy is? This is the amount of heat energy that is transferred during a chemical reaction. Chemical reaction. Now, you put this on your diagrams last time that you were working on, and it had units of kilojoules per mole. Now, what we use to represent enthalpy is delta H, right? We say delta H is our enthalpy, and it is approximately equal to Q. Now we're going to put an asterisk here because there's a reason why it's not necessarily equal to Q. It's only equal to Q at constant pressure. This is only true at constant pressure. But that's most of the time, right? That's most of the time. We're generally at constant pressure. So now we can come back to this delta H notation, this enthalpy notation. So this is sometimes used when we're given a chemical equation. And what it looks like is you have your reactants on one side, you have your products on the other side, and then at the end, not connected to your products, just a little after your whole chemical equation, there will be a delta H equals some value in kilojoules per moles. Now, for an exothermic reaction, since we're negative, this value should also be negative. This is like one of the hardest things for students to understand because they're like, you're creating heat. Why is it negative, right? Delta H values for exothermic things are negative. Now we could also write this in energy term notation. Right? And this is what I was talking about up here a little bit. Our reactants go to products, and in this case, energy is one of those products. So we write it in our chemical equation. We can put it in our chemical equation. Now, the last piece of the puzzle here is the energy diagram. And the energy diagram is something that you got a little bit of last class, right? You had to practice labeling the axes, drawing that energy diagram. So there's some key pieces that I'm going to point out for us today. For an energy diagram, our axes have our potential energy, which is those units of kilojoules per mole. And then on our x-axis, this is our reaction progress, right? It's as our reaction is taking place. And sometimes that's abbreviated with RXN, right? But our reaction is taking place, it's going on. So for an exothermic reaction, you can look back, right, at your own energy diagrams if you want. But the way that this looks is that if we're going to produce energy, if that's going to be one of our products, and our delta H is going to be negative, that means our reactants need to start higher than our product's end, right? So this is the energy of our reactants, which means this is the energy of our products. And we can label a few things on here. Now, last time you drew like a straight line going down, right? And labeled your delta H value. That's not actually how things work. If you go back into that simulation, you can click on the other diagram button and it will show you something that looks something like that. Now, you might be like, why do we have a bump here? What is that coming from? This is something that we call activation energy, right? And it's energy activation, right? So let's talk about that for a second. EA is our activation energy. And what that means is it's the minimum amount of energy needed to create products. Now the reason for this, the reason that we have an activation energy for things. Most of the time when reactions are taking place, we have to break apart something in order to put it all back together, right? We have to break apart our reactants to end up making our new products and putting those things together. Now, something that we learned, right, in terms of like breaking, even when we were just talking about like intermolecular forces, is that it takes energy to break those things apart, right? They're bonded together, they're attracted to each other, and so it's gonna take work to break our reactants up. So it takes some level of energy to break those things apart to then produce our products, and when we put them back together, they release energy. What we end up with is a difference between our reactants and products. This is that delta H value. And here we see that it's going down, so it's negative. Our activation energy is always between the reactants and the highest point of that graph. Okay, so now we're gonna go to the other side, right? And we're gonna talk about the opposite side, which is our endothermic reactions. Now, we already said that these feel cold. And the reason they feel cold is this is where heat energy is absorbed or required. So, if we drew our systems and surrounding again, if energy is flowing in, that means that this is going to be a positive Q value, and our surroundings is going to be a negative Q value. Now, we also can use the same notations for endothermic reactions. So if we talk about delta H notation, right, we have our reactants going to products, and then over to the side, we will have a delta H is equal to a positive kilojoule per mole value. It's important over here that we have positive enthalpy values for endothermic reactions. We can also use that energy term notation. Now, since energy is required, it's now like a reactant. So energy plus our reactant goes to products. I've had students ask me this before. They're like, well, can I write it as a negative value on the product side to show that it's actually an endothermic reaction? No, anytime that we're in energy term notation, you should write that enthalpy value as a positive thing on the correct side, right? Don't write it as a negative on the wrong side. This leaves our energy diagram. For endothermic reactions. Now, right, this looks very similar to our other one where we have the exact same axes titles, right? This is our reaction that's taking place. And then on our other, we have potential energy still in kilojoules per mole. But if we think about comparing this, if we have to have a positive delta H value, wherever our reactants start, our products need to end higher, right? So if we have our reactants, our products need to be higher. Now, similar to last time, we're gonna have a bump, right? That leads to our products. It might be a little bump, it might be a big bump. It depends on the reaction. But once again, we're gonna compare some very specific places. Your reactants to that bump, that's still your activation energy, which means that these types of reactions have really big activation energies. Your distance between your reactants and products, that is still your enthalpy value. If you're curious, the way that a catalyst works is that it lowers our activation energy in a reaction, which makes it easier to get from our reactants to our products. Now, that is all that we're doing in terms of notes for today. But if you've noticed, our kilojoules are per mole. Now, what this allows us to think about is our very favorite unit of the year, right? We've been talking a lot about moles all year long. And this allows us to take and bring out our last mole map addition. Now, this means that we can relate moles, there we go, here's our mole map. We can relate moles to energy. And the way that we do this is through our enthalpy delta H value. So, if you have your mole map out, zoom in a little bit. Our last thing that we can convert to is energy. We can now convert to energy, right? And the way that we do that is that our delta H value is equal to our molar ratio. Right? And that's important that we use our molar ratio, right? So whatever our number is in our chemical equation, those coefficients, that is going to be equal to our delta H value. You can also add that to the other side, right? We can convert to energy for moles of B as well, where our delta H is equal to the molar ratio of B. Now, I know that was a lot, so I hope that you took time to process everything. Feel free to rewind any part of this video. There is a worksheet up front which is titled Enthalpy and Dimensional Analysis Homework. This is what I expect you to be doing for the rest of the day, and it will be due next time I see you. The next time I see you, we are also doing our ice cream lab and doing a bit of review for our test, which is the following class period, right? So please be studying. You can be using that full semester long review. You can be using our unit reviews, but this test will be on gas laws, acids and bases, and energy. I know we haven't learned a ton of energy, so don't feel like that's going to be the majority of the questions, but it definitely will be a piece of that. Okay, so hopefully you found this enthalpy and dimensional analysis worksheet from up front. Now, the whole front side of this, problems 1 through 6, are using that endothermic versus exothermic stuff that we just learned, right? So it might ask you to write an equation in terms of the delta H notation or the energy term notation, or to use an energy term notation or delta H notation to draw what that energy diagram would look like, or tell me if this is an endothermic or exothermic reaction, right? So this should be pretty doable. This last one, you're labeling all the important things on here, right? Where are the reactants? Where are the products? What's our activation energy? What's our delta H value? Is this endothermic, exothermic, right? All those types of things. On the back, here's where it gets fun. Now, this is using your mole map, right? This is all that dimensional analysis that we just talked about. And so we're gonna do the first problem together so that you feel a little more comfortable with how this is gonna work. So our problem states, how many kilojoules of energy will be released when 4.72 grams of carbon react with excess oxygen gas to produce carbon dioxide? Now it tells us a few important things in our problem here. The first important thing it tells us is that we have excess oxygen, which means that is not going to be limiting. Our limiting thing, right, will be this 4.72 grams of carbon, right? And we're trying to figure out how much energy we make. So we look at our chemical equation that they give us here, and we need to balance that. We say we have 1 carbon, 2 oxygens on this side, 1 carbon, 2 oxygens on that side. So it's balanced, right? We have ones all along here. Now our delta H value is given to us over here, right? And this is our equivalency that we were talking about on that mole map, right? So we can go ahead and set up our dimensional analysis at this point. If you want to pull your mole map back out, right, and take a look at this, it's telling us, right, we're starting with grams, and we're trying to get to energy, right? We're trying to get to energy. So let's go ahead and do that. So our starting value, right, is that 4.72 grams of carbon. Now, to get from grams to moles, I need to use my molar mass, right? And 1 mole of carbon is equal to 12.01 grams of carbon. I find that on my periodic table, which now I can use my equivalency that I just came up with here. So I'm in moles of carbon on top, which means moles of carbon needs to go on the bottom. And my moles of carbon is this equivalency right here, that 1. So I have 1 mole of carbon, and that's equal to negative 393.5 kilojoules, right? That whole thing is the equivalency that I pointed out above. Okay, so let's plug that into a calculator, and if you do, you should get negative 154.647. And now we just have to sig fig, right? We have 3 sig figs in our starting value. So we keep 1, 2, 3. That 6 is going to round our 4 up, and we should get negative 155 kilojoules. And that's our final answer. Hopefully you feel confident now that you can go through a couple of these problems on your own. You should have about an hour left of class to be working. Please be careful on this last one. It is a limiting reactant problem, which means you should be solving it twice. As always, please reach out to any other teachers if you need more help, and I should be available by email. Have a great rest of your day.